There are quite a few important concepts in momentum, but it's more about the applications like collisions or situations where you have different masses. And at some point, you can even introduce the whole idea of center of mass or even rocket launching, right? Where you have a variable mass. Now, that's more in terms of analytical physics. So for this course, we focus more on situations such as bouncing balls, uh, cannons, like I'm gonna show you, or a person on a boat. So basically, two-body systems where momentum is conserved, or collisions where momentum is conserved, or situations of bouncing masses where you have a change of momentum and you wanna calculate the force, the next force acting, which eventually gives you the impulse. So the main equation that we introduced yesterday was the equation for linear momentum, which I said is a vector, so that's why it's written like this, with these units. So mass kilograms, speed or velocity, in this case, meters per second. So it's a vector because we care about the direction, right? If an object is coming down and then going up, when it's coming down, the momentum is negative. When it's going up, the momentum is positive. So the overall change of momentum, right? If we assume the velocity, or in this case, the speed, the magnitude to be the same down and upwards, then it will be 2mv, which is not really the case, right? If you bounce balls on the floor, they never reach the same height. And that's because there is always loss of energy, which you're gonna see. Well, I mean, it's due to this force that is acting on the on the ball, right? So there is some work done, and work is change on energy, right? It can be change on kinetic. In this case, change on kinetic energy. So change on kinetic energy means that the speed of the mass is not going to be the same, right? There is a change. Additionally, the net force acting on the body is the rate of change of momentum, right? Momentum is mv. If you do the rate of change, mass is constant, so that's why I said we focus more on constant masses. So mass doesn't change, but the change on velocity as a function of time is the acceleration. So it's another way to write Newton's second law, and then if there is a net force, then we define that also as the impulse. Impulse is change on linear momentum, which is equal to the average force acting on the mass multiplied by the elapsing time, right? If there is a collision, right, there is some time. For example, here, if you have a person who is hitting a baseball, right, there is initial momentum, final momentum, and the momentum is not conserved because the baseballer is exerting a force which is acting on the mass, right? So you may produce a large force acting for a short time or a smaller force acting for a longer time. And that makes sense based on this, right? If you increase the force, you lower the time. Or if you lower the force, the time has to be increased. That's because they are inversely proportional, right? And then we spoke about the conservation of linear momentum, where if the net external force acting in a body is zero, right? Then the momentum before or after a collision is the same, right? Now, the net force acting on a system is always the sum of the external forces. That's because internal forces act between objects within the system. So always the sum of internal forces is zero. So we don't worry about internal forces. We focus on external forces. here the external force is not zero because the external force is causing the change, right, in the velocity, which eventually is a change of momentum, and that's why you have this, right? A change of momentum gives you a net force. But if the sum of the external force or the net force acting on a system is zero, then the change on linear momentum is zero. That means the momentum, the initial momentum is equal to the final momentum. Okay, and that's an example here that we're also gonna do. All right, so we have action reaction, right? A person is pushing a boat with 46 newtons, and by reaction, he also feels a force of 46 newtons acting on his hand. So the net force acting is zero. So we have a conservation of linear momentum, where the momentum of this boat, the change of momentum on this boat is equal to the change of momentum of this boat, right? You have two boats here, but you can also think about that as one boat. Like for example here, right? You have a person who is throwing a mass, right? And by a conservation of linear momentum, the person on the boat is gonna recoil to the left. It's the same effect as when you shoot a gun or an arrow, right? There's recoil that you feel on your hand because of conservation of momentum. We explained that by using Newton's third law before, which makes sense because action reaction. But now we can quantify by how much there is recoil, right? You can have the conservation of linear momentum in situations like this as well. Two masses attached by spring, and it's compressing the spring, so you have two masses compressing a spring, and then you let it go, and they move in opposite directions. So we're gonna also go over a situation like this, and then you may have well, this is what we did yesterday, right? And a situation like this, right? Like a cannon launching a bullet, and then by the action of that, the cannon is gonna recoil to the left. So physically, the situations will make sense. It's nothing it's nothing new, but we're gonna learn how to quantify that using conservation of momentum or and also in some cases conservation of energy, right? Let's see if this works. Yeah, so this is fire. Yeah. Okay, so let's show you this, right? You have a big mass here, which I can change. I mean, it's 4 kilograms. Make it smaller. Oh, great. Freaking okay. And with the mass of this, we're talking about 75 grams here. Yeah, yeah, that's okay. Leave it like that. So if I look, that's a lot, right? Let's say we have 120. So if I fire, the bullet is stuck inside the mass of wood. And as you can see from this dash line, or here, it goes up a little bit, right? Let's reset this. Well, I'm gonna make up the numbers, I think. So yeah, it goes up because of conservation of both linear momentum the momentum of the bullet, it's basically transferred to the momentum of the whole system when they stick together, and they both gain some velocity. And by conservation of energy, the kinetic energy, when the bullet strikes here, the mass, it continues lifting it to a certain height. And that's why you have an angle here. All right. So that's another example. That's the ballistic pendulum, right? So the main equation for this chapter is the linear momentum equation, you repeat. Then you have this, which is more like a way to rewrite Newton's second law. Then you have the definition of impulse and the impulse momentum theorem. That's one way of describing this. The impulse is equal to the change in linear momentum. So there. And all of these quantities are vectors, by the way, except time. Force is a vector, you know that, it has magnitude and direction. Momentum is a vector, and because of that, impulse is also a vector. All right. So the collision that you just saw is a perfect or complete, perfect or complete inelastic collision, because you have masses that stick together after the collision. There is inelastic collisions. Inelastic collisions are the most common type of collisions that you observe. It's a collision where only momentum is conserved, no energy. Yesterday, I spoke about elastic collisions, where both kinetic energy and momentum are conserved. Those are not very common, although we try to replicate them in labs, right? And we're going to solve problems using elastic collisions because by having both situations, kinetic and momentum conserved, it's easy to solve for a missing value. Like if you are looking for the missing velocity, right? Or if you are looking to find in this problem, for example, that you have in front of you, right? You have a mass which is moving towards another mass that is at rest. And then after the collision, they both keep moving to the right. That's an easy problem to solve because it's an elastic collision, so momentum and energy are conserved. So we're not going to memorize any equations. I'm going to show you how to solve them using the conservation of momentum and energy. And then you have collisions in more than one direction. Now you can have collisions like this. So we can find the net velocity and the direction, especially if you assume the masses to be the same. So we're going to do problems like this. And then also using elastic collisions, we can do problems like that. All right. So that's the idea behind collisions and linear momentum. Okay. A lot of applications, so we're going to start doing those now. And then at the end of the class, I will start with concepts of the next chapter, which is rotation and kinematics. All right. It's important because you're going to have an exam on chapter 7, chapter 6, chapter 7, and the beginning of chapter 8 next week. All right. So chapter 6 is not very long. We're going to do problems right now. You're going to see how they work, what are the parameters, what are the strategies, okay? And then we can start talking about chapter 7, which starts with a few new concepts, right? The whole idea of angular velocity, angular position, and then eventually talk about gravitation and rotational equilibrium. So torque, moment of inertia, which some of you are going to see tomorrow in an experiment. All right. So unfortunately, I won't be able to talk about moment of inertia before tomorrow's lab, but I will at least show you what that means. So at least you know what that is about before we cover it in the lecture. All right. Okay. So let's show you some strategies here. This one here, right? And I kind of did this problem yesterday where you have a mass being dropped from a certain height and then it's bouncing or rebounding from the floor, reaching this height. So like I said, the ball doesn't reach the same height because of the impulse. All right, so there is a force acting on the ball. So let's do this. All right. So in this problem, you have a mass or a ball that is being dropped from certain height. And you have the mass here, 0.150. And it's gonna reach the ground. And it's gonna bounce back to a height that is less than the first. The two heights are 0.96, 1.25, 0.960. So these are initial height. And this is the second height. And of course, you have gravity. So they're asking you, what's the impulse by the floor? Okay. So we're going to find the impulse. If they ask you a question like that, you just want the magnitude, okay? The impulse is equal to the change of linear momentum. So the change of linear momentum is equal to P final minus P initial. That's pretty much what you have to do. Okay? P final will be when the ball was here. When the ball was here, it went up with V2. And when the ball reached the ground, it reached the ground with V1. These are not the same because of this. So to find V1, we use conservation of energy. This is a rest. You're dropping it, so it's a rest. So the potential energy, if I make the ground my reference, the potential energy is mgh, which is 1.25. And that's equal to the kinetic energy when it reaches the ground. So we don't need a mass, and we find V1 as the square root of 2g times 1.25. G is 9.8. Like that. So the speed, the speed, right, is about 4.95 meters per second. So now I can find my initial momentum. I have mass V1. So P initial, vector-wise though, is mass times the velocity. But this velocity, right, because it's going down, is negative. So I just find the negative 743. There. Kilograms meters per second. All right. So that's my initial momentum. I need a final though. To find the final momentum, you need to find V2. Now, to find V2, you need to use information that the mass bounce back to this height. So, just like I did here, I use conservation of energy. The kinetic energy right after the collision, this kinetic energy, is equal to the potential energy here, which is mg, and now is 0.960. So the masses again cancel, and V2 is the square root of 2 times 9.8 times 0.960. All right, so I found, or I can find now, the V2. $4.34. Makes sense because it's lower than the initial. So I have V2, so I can find P final. That will be the mass times the velocity, positive because it's going up. That times 4.34. If I multiply these two quantities, I get 0.651 kilograms meters per second. All right, so now the impulse is P final minus P initial, but hey, wait a second though. P initial is negative, so minus plus 0.743. And that gives you 491.394, which I guess you can write to 1.39 kilograms meters per second. All right, there. So that is a great example where we use energy conservation and the momentum impulse theorem, or the relationship between linear momentum and, of course, impulse. All right. I will just say you just have to be careful with the signs, but we use concepts from before and a new concept right now, which is linear momentum. I don't think is anything that that should fly over your head. I think it's everything that we've been doing. All right, and then we'll see if we can check here. Yeah, 1.39. There you are. Okay, so that's a bouncing ball example there. Now let's do a tennis racket. There it is here. So now that's a horizontal situation. We're gonna assume it's horizontal. So a tennis player receives a shot of that mass horizontally traveling at 50 meters per second and returns that shot at 40 meters per second in the opposite direction. What's the impulse delivered to the ball by the racket? And now they ask you, what work does the racket do on the ball? That's an interesting question because where does the work come from? The work comes from the change on kinetic energy. Since first is traveling at 50 and then is traveling at 40, there is a change on kinetic energy. That's due to the work done by the racket. Right? Remember that the racket exerts a force. So there is impulse, but there is also work done by the racket on the ball. All right. All right. So let's put it here. You have a tennis ball traveling at 50 meters per second. And then is shot back at 40 meters per second. This is easier than the previous problem because they already give you the velocities and the mass. 0.0600. Oh, units of sig figs there. 0.06 kilograms basically. Now let me see. Oh, 40 points. So this is only free sig figs, so we don't have to have free sig. Okay. Doesn't matter. Yeah, the values. It's also gonna be the value. So the impulse is P final minus P initial. Now, because I assume it to be like that, my P final is 0.0600 multiply by negative 40 minus my P initial is 0.0600 multiply by 50. So I can factor this out. Negative 40 minus 50, negative 90. So negative 5.4 or 40. That's okay. Kilograms meters per second. If you want to know the magnitude of the impulse, because that's a vector, is just 5.4 kilogram meter per second. So that's easy, right? What about the work? Work in this case is a change on kinetic energy. That's the work energy theorem, right? We've done that. So energy final minus energy initial. Energy final, well, kinetic energy final is 1/2 of the mass V final square minus 1/2 of the mass times V initial square. If I factor out, I get 1/2 m V final square minus V initial square. What's V final? Negative 40. What's V initial? 50. But because we're squaring it, doesn't matter the sign. 1/2 0.06 or 600 multiplied by negative 40 squared, so 1600 minus 50 squared, which is 2500. So what do we get? Okay, so 1600 minus 2500 multiplied by 0.06 divided by 2, negative 27 joules. So it makes sense. There is a loss of energy. The work done by the racket is negative because the force acting on the ball is towards the left. That's why. All right, so there you have it. Energy, work, and of course, impulse and momentum.
Quick question.
Yeah.
Which formula did you use to get impulse?
Impulse is the change on linear momentum here. So I wrote it down. Impulse is delta P. So P final minus P initial.
Okay, thank you.
So if they don't give you force or they don't give you time, you have to use that. All right. Let's do this one. What happens if you're giving angles? And then we can do collisions. All right. So sometimes you can have situations like this, more realistic, right? When you bounce balls at a given angle. Now, what's not realistic is that the angles are the same and it's the same speed, right? 10 meters per second. So whatever. It's an elastic collision, that's why. A 3 kilogram steel mass, like the one you guys used yesterday, is bounced on the wall at this angle. And the ball is in contact with the wall for 0.2 seconds. What's the average force exerted by the wall on the ball? So for this problem, you need to break the velocity into components. Why do you need to do that? To realize that only one of the components is responsible for the impulse, change of momentum, and therefore the average force. Okay. So you have, yeah, they need to do this. There you are. So you have one going like this, and then bouncing like that. Same mass, 3 kilogram. And then the speed is 10 on this direction, and then bounces like this, right? Like this, and like this. The angle is the same, 60 degrees. So if you break into components, look what happens. One component like that, and one like this. For the one going up, you have one component like this, opposite to this, and one going like this. Because this is the same. 10, 60, 10, 60. Let's use this angle. 30 degrees. 10, 90. This is the adjacent to 30. So on X, this is 10 cosine 60, cosine 30. And this, again, this is 30. This is 10 cosine 30. So like this is 10 cosine 30. Like this is also 10 cosine 30. But they are in opposite directions. However, for the vertical, This is tensine, both going up. So there is no change on linear momentum when for the y component of the velocity. There is not. This is like I said, 10 sine, 10 sine, 10 cosine, 10 cosine. So let's write here. B initial on x is 10 cosine 30. B final on x is negative 10 cosine 30 because it's going to the left. So then they're asking for the force. Change on momentum, because different velocities, is equal to force times elapsed time, which is 0.2 seconds. The mass is 3 kilograms, so change on momentum is mass B final minus B initial. B final minus B initial. Okay, so I can factor 10 out, and I get negative 30 times 2 cosine 30. $1.73. And if I multiply that by 30, negative 52. That's my delta P. All right, negative 52. But they ask you for the force. The elapsed time is 0.2, so to find the force, F times 0.2 is equal to this. The force equals to negative 260 newtons. Does this make sense? Why is it negative? Because the force is acting towards the left. What about the vertical? Like I said, vertically, there is no change of momentum. The velocities are the same. Okay? So that's another nice situation there. Now in two directions. So you see breaking vectors into components, and knowing what's happening, it's important to solve these problems, all right? There is at least one more example I'm gonna do on momentum, but let's show you how to solve problems with collisions now. Perfect inelastic and elastic, all right? Now, before I do that, are there any questions about this? This is kind of what we did yesterday. I'm just going over a couple more examples, 3 more examples. You even saw today one with an angle there. Just so you see how everything that we did before relates. Okay. All right. collisions. I'll do this one after. All right, let's do this. A man of mass 70 kilograms is skating at 8 meters per second behind his wife, who has a mass of 50 kilograms, skating at 40 meters per second. So they both are skating on the same direction. Let's say to the right. It says instead of passing her, he collides with her, and he grabs her, and they keep moving together. So what type of collision is this? That's a perfect inelastic collision because they stick together, kind of, right? They keep moving together after the collision. So how can we find the final velocity of both of them after the collision? All right. So this is a conservation of momentum situation. The way you can sketch the problem, you can just do it like one mass, 70 kilograms, moving at 8 meters per second, positive, so to the right, who is about to collide with a 50 kilogram, with his 50 kilogram wife, who is moving at 4. Yeah. This we call it before the collision. I showed you this yesterday, so we're doing this again, like how we label this before the collision. Then the after will be both of them together. Traveling at BF. You want to find that final speed or velocity. So, for any type of collision, you will always use the conservation of linear momentum because the net force acting on the system is 0. So, before the collision, you have mass times velocity plus mass times velocity. So 70 times 8, positive both, plus 50 times 4. That's equal to, that's the momentum before the collision, that's P initial, or P before. That's equal to P final, or P after, which is M1 plus M2, so 70 plus 50, 120 times B final. And that's how you solve this problem. You get 560 here. You get 200 here. That's equal to 120 BF. 560 plus 200 is 760. 760 divided by 120. That's BF. So BF equals to about 6.3 meters per second. So it takes more time to do the sketch and to do the whole reasoning. Yeah, 6.3 there. You don't need this, so just that, and then perfect inelastic. Perfect inelastic collisions are really simple because the masses stick together. So there's not really much to say. Like the situations are very simple, and there are many situations with like the ballistic pendulum is a right. It's a perfect inelastic collision, but you can have situations more complex like this. But before we do this one or this one, let's do an elastic collision. So no, that's in two directions. Let's do one. Still have one here. Ah, there it is. This one here. There are different things that they ask you. A 2-gram particle moving at 9 meters per second makes a perfect elastic. So not perfect inelastic, it's a perfect elastic head-on collision with a resting, so at 0 velocity, 1-gram object. Find the speed of each particle. All right. So this one is a bit more, not difficult, it's just different. So now let's do, caramba. Let's do elastic collisions. All right. So in that problem, they are giving you one mass approaching a 1 gram, and then after the collision, we're gonna assume the mass like this, and then like this. All right. This is 2 grams, 1 gram, 1 gram, 2 grams, V1. Well, they give a V1, right? 9 meters per second. Okay. So this is at 9 meters per second. This one is at rest. So V2 in, yeah, V2 is 0. V2 initial, or yeah, initial. And then here, let's call it V1 final. And this one, obviously, to the right, V2 final. This is a direction I'm assuming. So I'm going to highlight this. I'm assuming this. We'll see what the math tells us. So there are two variables. So how do you solve a problem where you are given two variables? Well, elastic collisions have an advantage. You have both the conservation of momentum and the conservation of kinetic energy. So that means that by conservation of momentum, so first, let's write down the conservation of linear or this momentum, right? So my momentum here, this is before the collision, and this is the after. All right. Before the collision. And you know what? Because all the masses are in grams, you can leave it in grams. It will cancel out. The units will cancel out like this. Look. 2 grams times 9 plus 1 gram times 0 equals to the momentum after 2 grams times V1 final plus 1 gram times V2 final. So grams will cancel. Grams will cancel, and even the velocity. But this cancels. 2 times 9 is 18. And you have your first equation here. 2V1F plus V2F. All right. So that's my first equation. Now, let's write down the conservation of energy, of kinetic energy. All right. So, kinetic energy, no kinetic, kinetic. So, 1/2 times the mass times 9 squared plus no kinetic, so 0, equals to 1/2 of the mass V1 final square plus 1/2 of the mass times V2 final square. So again, the masses will cancel, the units don't matter because they cancel. 0, that's 1, 9 squared is 81. Again, this cancels here, and then you get V1 final square plus 1/2 V2 final square. I don't like fractions, so I multiply by 2. 1, 6, 2. 2 is equal to 2 V1 final square plus, I multiply by 2, so this drops this V2 final square. All right. Second equation there. One equation here, another equation here. So that's the physics behind this problem, right? Conservation of momentum, conservation of energy. The conservation of energy is easy. You don't have to worry about, well, even the momentum, because, I mean, this one was not moving. So that made this easy. So now you have to solve the problem using math. And this is a quadratic equation. It's a linear equation, so you have to solve one variable in terms of the other. The strategy is pretty obvious. V2 final, let's write V2 final in terms of V1 final, and let's substitute that in here. And then you get a quadratic equation. All right? Sorry, guys, I have a question here. All right. 18 minus 2V1F, so V2F is 18 minus V1F minus 2V1F. All right. So this is from the conservation momentum. This goes here. So you have to be very, and that's why I noticed when you guys do this in the lab, I want to be honest. You have to be really organized, right? Like you don't have to rush, just do it patiently. You see how I'm doing it? Square plus, use parentheses, because you have a whole expression here. 18 minus 2V1F squared. Sorry, 2V1F parentheses and then all squared. So let's actually, there. All right, and then it's just algebra. So I always tell my students, right, you complain about algebra, it always comes back. Quadratic equations, for especially. V1F squared, and then this is a binomial, right? So 18 squared, 324, plus this value squared, plus 4 V1 final squared, minus 2 times 18, 36 times 2, 72 V1F. Okay, so perfect. 4 plus 2V1F, that's 6V1F squared. Yeah, so I will send this to this side. So 0 equals to 2 plus 4, 6 V1F squared minus 72F V1F plus this minus that. That will be 162, right? Yeah. Okay, look. 6, 72, 162. I can divide by 3. That's 2V1F squared minus 3 times 2, that's 24. No, yeah, 24 V1F plus 3 times 5, 50, 50, 54. There you are. Just to make it more simple, I can keep dividing this thing. Divide by 2 now. So, because half, half, half. So V1F squared minus 12 V1F plus 27. All right. So, can I even factor this? 9, 3. Oh, yeah. So you can use the quadratic equation, or if you think about it, 9 and 3, right? 9 times 3 is 27. And 9 plus 3 is 12. But if you want to just do the quadratic equation, you can just do V1F is negative V plus or minus the square root of B squared, which is 144, minus 4AC over 2A, which is 2 times 1. So you're going to get two values, guys. V1F can be either, and they give you the both solutions that are possible. It can be either 9 or it can be 3 meters per second. So which one is the one that makes sense? So we go back to the problem. And yeah, it doesn't make sense for V1 final to be 9, right? Because it was 9 before and there was a collision. So the solution that makes sense is 3 meters per second. The other way you can figure it out is by looking at this equation to solve for V2F. Once I have 1F, I can solve for V2 final. V2 final is 18 minus 2 V1F. If V1F is 3, 3 times 2 is 6. So V2F is 12. All right. So I have the velocities. That's how you find them. All right. If this was 9, that means V2F is 0. That doesn't make sense. Right? Furthermore, if you think about it, right? V2F is 12. So if V2F is 12 meters per second, this velocity has to be going to the other direction. 3 meters per second. Why, you may ask? Easy. 12 minus 3, 9. So physically, that's how it goes. All right. That's basically what you get. All right. That's the main idea with that problem. So what is the only difficulty here is that you have momentum and energy conservation. And then you have to be careful with how you solve the problem. All right. It's just algebra at the end of the day. So any questions about this particular example? Where is it? Here. And that's in the Web of Science. So you're gonna have the problem there to practice it. All right. You have elastic and perfect inelastic collisions in the assignment. Let's see. Let's do this in 2 directions. So you can see the difference between this one was in 1 direction. So you can use this. What happens when you have, and to be honest, it's actually easier. This. All right. This is probably what you see when you play hockey, curling, or even pool. All right. You have before the collision, after the collision, and it's elastic. You know how you know? Just to give you extra information as well, by the angle. The angle here is 90 degrees, 37 by 55. So in a 2-dimensional collision, this is 2 dimensions, X and Y. If the angle after the collision is 90 degrees, that's an elastic collision. Okay. So, and after that, I can give you a small break, all right? So you have 2 disks, both with the same mass. One is moving at 5 meters per second, one is at rest. So similar to the previous one, but after the collision, they bounce at different angles, different directions. Determine the speed of each disk after the collision. So the orange and the green after the collision. All right. So the advantage of this is that in X and Y, you have the momentum both on X and on Y. So the equations are just linear. In fact, let me show you with this. Okay, let's see. Should I draw this? Yeah. Before the collision, like that. And it has to be at a certain angle. And then you have they have to give you a reference line because that's the reference of the collision there. One goes like this, so one goes like this. Okay, 3753. M and M. They both are the same mass, so. And this is going to have 5. Yeah, okay. So this is a rest. That's what makes this problem not so bad. Now, what I'm going to add is this. Because you have to break it into components. You are going to do conservation of linear momentum on X. So we are going to call this V1. And V2. You can break this into components. So you have V1X and V2X, but look what happens on Y though. On Y you have it like this. V2Y, V1Y. And because it's a collision, momentum is conserved on X and Y. So my momentum on X is M times 5, so mass times 5, plus 0, M times 0, equals to mass times V1X plus mass times V2X. So mass cancels, that's why they don't give you the mass, it's 0. So you get the first equation, 5 is V1X plus V2X. Now, V1X is V1 cosine 37. And V2X is V2 cosine 53. Oops. So that's my first equation there. This. That's on X. Now, we do conservation of linear momentum on Y. On Y, there is no component here. So before the collision is 0 momentum on Y. For both. There's no moving, so there's nothing on Y. But here, now they give you the directions now. So MV1Y is positive minus MV2Y. Well, M cancels, and then you get V1Y has to be equal to V2Y. But we know that V1Y is V1 sine 37 and V2Y is V2 sine 53. So two equations, two variables, and linear. Just linear. I want to approximate this, right? So V1 sine 37 is 0.6. V2 sine 53 is 0.8. Okay, so what I get is that 6V1 is equal to AV2. Or V1 equals to 8 over 6, which is 4 over 3 V2. Why do I need that? Because then I can use this in here. Now, 5. So the momentum equation, 5 equals to V1 cosine 37, which is 0.8, plus V2 cosine 53, which is 0.6. You can check in the calculator. I'm just rounding it to keep it more simple. But I have V1 equals to this, so I can replace this here. So 5 equals to 4 over 3 times 0.8. Don't forget about that. V2 plus V2 times 0.6. Let's find all these factors. So 4 over 3 times 0.8, that's 1.1. Okay, so 1.1, right, this is all 1.1 plus 0.6, so that's 5 equals to 1.7 V2. All right, nice. So V2 is 5 over 1.7, 2.9 meters per second. If I have V1, V2, I can solve for V1. V1 is 4 over 3 times this. So 4 over 3 times 2.9. 3.9 meters per second. There you are. The answer's here. No. So elastic collisions in two directions. I believe it's easier because you only have to use momentum. Momentum on X, momentum on Y. Again, very important, the whole vector, sine, cosine, knowing the directions. That's why it's negative here, because of this direction. All right. Two-dimensional or collisions in 2 dimensions. Not very popular in exams. Like, barely see this in exams, but it's actually not bad. It's actually not bad. I feel like many students just or some professors they feel like because of the vectors, but it's not bad. It's actually easier than the one dimension. All right. And as you can see, once you set up the equations, half of the problem is just solving for V's or doing the math. So are there any questions before we go on break? Okay, so I'll give you a 10-minute break and then we continue with some collisions, and then I think we can start chapter 7 after sometime after 8, at least the concepts, so we can talk about the math tomorrow. All right. I want you to take a look at the following situation, 42. You have a bullet with mass a gram, so it's like the ballistic pendulum, but now the block, right, is gonna fly in a projectile motion direction or trajectory from 1 meter high. So it's very similar to what you guys saw in the experiment, right? 1 meter high, the table. Now you have the bullet with a similar mass, and they both end up landing at this point. So how will you find the initial speed of the bullet? Since some of you are still like probably coming back, I'll give you a few minutes to think about it. You have a collision first. It's a perfect inelastic collision. And then it flies. Look, think what you did in the experiment. What did you do? This is the range, this is the height. So, and I want you to find the speed of the bullet. So yes, this is a good situation to review what you guys did. Again, I will calculate the time, the flying time. And then with that, you can find the speed of both after a collision. And then from that, you can go backwards to find the speed of the bullet. So did anybody find the time? You can use a chat if you want. Nobody? All right. So to find the time, you want to use the height because this is at rest. Vertically, there's no speed, so you can find the time. And no, you don't want to use energy for this. You want to use motion and momentum. Okay. Put this away. You see how the height is 1 meter? You're going to do 1 meter equals to 1/2 g times square. So solve for time. And then, since you have the flying time and you have the range equals to v times time. So solve for v. Yeah. So you got the time, 0.45 seconds. And the velocity 4.44. Okay. So this velocity meters per second, right? Is the one after the collision. So use conservation of momentum is a perfect inelastic collision. So these stick together, right? Use the conservation of momentum to find the speed of the bullet. So for that, aim of the bullet, uy, caramba. Aim of the bullet times the speed of the bullet equals to aim of the bullet plus the mass of the block times V, which is this. So did anybody find V of the bullet? That the mass is there. You don't even have to change the units for mass because they cancel. Hmm? 8 grams mass of the bullet, 250 mass of the block. So if you divide here, you get 8 plus 250 in parentheses over 8 times 4.44. Like I said, the grams will cancel, so I don't have to change the units. What do you get if you solve this? Yeah, 143.2. There you are. So as you can see, we can combine, right? We use, this was a momentum, chapter 6 topic. This was what you should know from chapter 2, chapter 3, motion. All right. Okay, let's do one that is a bit more difficult. Again, since it's on the assignment, I'm gonna let you guys kind of work it out. I'll give you some hints, of course. Where are you? This one is good. I didn't put this one, but this one is a good problem as well. This one we're gonna do next chapter. This one is similar to what we just did. That one is like that we just did. Where is it? Ah, this one. So the two masses compressing the spring. You have two masses and they are compressing the spring by 9.8 centimeters. And then you let them go and they go in different directions. Neglecting the mass of the spring, find the velocity of the masses after. This is the first thing that you have to do. The momentum here, guys, when the masses are not moving, right? What's the momentum of the system here? What's the momentum on A? If they are not moving.
0.
Yeah. And then there is momentum here, right? After, because they're moving. Now, what force is acting on M1 here? Like, what's making M1 move like this? What's pushing M1 to the left? What's pushing M2 to the right?
Would it be the force of the spring, K?
Yeah. And is it the same for each mass? Is the force the same for each mass? It's the same spring. So what do you think?
Yeah.
Yeah. So, but the force is acting one to the left, one to the right. So they cancel. The net force of the system is 0. Not for each mass, but for the system. So if the net force is 0, the momentum is conserved. So the momentum here is 0. That has to be equal to the momentum of this. But this one has momentum to the right. This one has momentum to the left. So you want to write conservation of momentum. Just be careful with the signs. So that's the first equation. The second equation is you are neglecting the mass of the spring. You are neglecting friction. So there is conservation of energy. Okay, on A. What's the energy on A? When the masses are compressing the spring. What's the only energy on A?
Elastic potential?
Elastic potential, yep. And once they move to the right and to the left, what's the energy on B?
Kinetic?
Kinetic. So potential elastic is equal to kinetic energy of M1 and M2. Two equations with two variables. That's how you do it. So go for it. I think at least to write the equations, I'll give you like what? 5 minutes. All right. And then I'll be asking, because that problem is on the assignment, I want to make sure that you guys understand how to do it. Different numbers, of course. You want to use meters, by the way, so you want to change this to meters. The mass is already in kilograms. That's already indicated. So let's see. Okay, while you guys are doing that, just as a reminder, on Thursday, you're gonna have just chapter 6 quiz. So whatever we do later today or tomorrow, or even on Thursday, is not gonna be there. That's chapter 7 and 8, or chapter 7. So it's gonna be an easy quiz, short, just 6 questions. And then the exam, chapter 6, 7, 8, that will be next week. All right. So make sure you are doing this assignment and taking notes of these problems. I mean, it's not that different to what we did before, but still. Okay, did anybody write the conservation of momentum? What will be the equation for it? The momentum before, guys, is equal to what? We said it already.
0.
0. So we write 0 after 0 equals to what? M2V2 minus M1V1. So M2 is 0.88, V2 minus 0.56, V1. So that's why you need it, because just like this problem that we did before, right? We can write V1 in terms of V2. So I get 0.56 V1 equals to 0.88 V2. So just to make it easier, V1 equals to, oh yeah, I close it. Just divide 0.88 over 0.56, about 1.57 V2. Is that clear? Is that clear for everybody? Like the momentum conservation? Yep. Okay. What about the energy? Elastic and kinetic. So what will be the equation for the elastic energy? Energy initial. Yep. What's the equation? Or what's the expression?
Is it 1/2 kx squared?
1/2 k x squared is 0.098, right? Oh, sorry. Yeah, 0.098 squared. All right, that's the only energy. What about the energy kinetic? For M1 and M2? For M1 is this. For M2. How about that? Ha, look, half, half, half. And this is a number. $2.69. 0.56 V1 squared plus 0.88 V2 squared. Is that clear? Questions? No questions? Sure? So now you just have to solve for V1 and V2. You have V1 equals to 1.57 V2. Plug this into here. Again, you have to do it step by step. V1 square 0.88 V2 square. All right. Somebody tell me, what do you, like, do the math. What do you get for V2? Hmm?
1.09.
1 point what?
09.
1.0. Okay, let's double check. 0.88, 0.26, yeah. 1.1. Very good. 1.1 meters per second. Perfect. That's V2. And then V1 is 1.57 V2. So 1.73. How about that, guys? Any questions about this? For this problem? The advantage of the book is that they give you this information, but it's kind of what I'm explaining, right? You have conservation of momentum and conservation of energy because the net force acting on the system is 0. And there is no friction, so there is conservation of kinetic energy. All right. All right. So my suggestion is that you practice with them.